So hello and welcome back. So in this video we want to define exponential functions, which is the section on page 464. And here the language of the book sometimes gets a little bit tricky. So I'll try to go over each sentence and see if there is something that needs explanation. I'll try to explain that. So let's start with the study. The study found that the percent of the population who are vegans in the United States doubled from 2009 to 2011. So basically you can build this table, and this is T time in years, and this is the number of vegans. Let's call it V of T as a function of time. So what's happened here in 2009? In 2009, I don't know what the population was, so I'll just call it X. In 2011, so 2 years after that, I'm sorry, 2011, the population was doubled. So it's basically X times 2. The population that I had in 2009, and that has been doubled. So in 2009, 2.5% of the population was vegan, adhering to a diet that does not include such and such and such. So that basically means that this X times 2 was 2.5% of the population of the US in 2011. Now they go on to say that if this rate continues, vegans will make up 10% of the US population in 2015, for example. So if the same rate continues again after 2 years, so in 2013, for example, this output will be doubled as well. So again doubled, so X times 2 I had here, and again times 2. So whatever the population was, it's again been doubled. And again the same thing happens after 2 years, 2015. This population is going to be doubled, so whatever it is, X times 2 I had here, again times 2. So and this is basically, well, that's not important how many years have passed. For now we just don't need it. And they say that in 2015 this is going to be 10% of the population. And that's basically that is basically because here you can see that the population was X times 2, and here was X times 2 times 2 times 2, so times 4 basically. So here I had 2.5%, 2.5 times 4 is equal to 10%, and so on and so forth. So you can extrapolate this table to go on to 2019, 2050, and so on and so forth. Of course, assuming that the same rate of change is going to happen throughout all the years, all the way up to 2050. So all the way up to 2050 here. Up to 2050 is going to be it's going to be 80%. So this is basically an exponential function that grows over time like this, and you already know almost everything about it. Now there are a few terms that you need to understand here, and the percent change refers to a change based on a percent of the original amount. So I'm not sure what they are referring to, but as we go along I'll get more information on that. But there is another term here that we have exponential growth we have exponential growth, and also we have exponential decay. So basically exponential growth is the case that, for example, you have this population in 2009, and then in 2011 the population is whatever that was, it's doubled, multiplied by 2, so it's basically growing. But you could have other models. For example, the population of some species of animals in some place on Earth. So in T, for example, let's say this is the species S of T, and let's say again in 2009, let's say the population was X, and then you could say this species after 2 years, for example in 2011, the population is X times 1 by 2. So here, instead of multiplying the population by 2, I'm multiplying by 1 by 2. That means the population has been cut in half. And the same thing if keeps going on, it's in 2013, for example, it's X times 1/2 times 1/2, and so on and so forth. So this is an example of exponential growth, and this is an example of exponential decay. So here you can see that the population is decreasing and decreasing. In this case, you have a graph that looks like something like this. Something like this. The population is decreasing. In this case, you have a graph, and the population is increasing. Something like this. So this is growth, and this is decay, and both of them are of course exponential models. So now next, what we need to understand here, let's contrast exponential growth. Okay, so in this section they have given us a model which is a pretty good model to compare exponential functions to linear functions, which we can do, and it's actually interesting. So let's do that as well. So basically what we have here in this comparison is that we have basically two functions. So let's call these, they've been called f of x and g of x. So this is your x, and this is your f of x, which is equal to 2 raised to the power x. So this is an exponential function, and you have another function g of x, which is equal to 2 into x, or 2x. So this is a linear function. So I can input different values into the two functions and see what sort of outputs I'm going to get. For example, let's go with the same example in the book and go from 0, 1, 2, 3, 4, 5, and 6. And in the case of this exponential function, you have 2 raised to the power 0 is equal to 1. So this is the output of the function for this input. And for x is equal to 1, this is 2 raised to the power 1, which is equal to 2. 2 raised to the power 2 is equal to 4. 2 raised to the power 3 is equal to 8. 2 raised to the power 4 is equal to 16. 2 raised to the power 5 is equal to 32. And 2 raised to the power 6 is equal to 64. And for this function, you just multiply this 2 into each of these inputs. So 2 into 0 is equal to 0. And then 2 into 1 is equal to 2. 2 into 2 is equal to 4. 2 into 3 is equal to 6. 2 into 4 is equal to 8. 2 into 5 is equal to 10. And 2 into 6 is equal to 12. So you can see that this basically we have the same increments in the outputs. Basically every time I'm incrementing my input, in the inputs, every time I'm incrementing the inputs by 1, 0 to 1, 1 to 2, 2 to 3, to 4, 5, 6, and so on and so forth. And each time the output of the function is being multiplied by 2 here. So for example here, the output of the function is 1, and 1 multiplied by 2 is equal to 2. 2 multiplied by 2 is equal to 4. 4 multiplied by 2 is equal to 8. 8 multiplied by 2 is equal to 16. 16 multiplied by 2 is equal to 32. And 32 multiplied by 2 is equal to 64. So this is how an exponential function behaves. Every time you increment your input by a fixed amount, in this case for example 1 unit, your output is going to be multiplied by a fixed amount, which is called, I keep forgetting this, I don't exactly remember the term, but it's the output is always being multiplied by a fixed amount, and that basically creates the next output of the function all throughout the function. And you can see that in the case of this function, the output is growing very rapidly. But in the case of this function, g of x is equal to 2x, this is a basically linear function, a straight line with slope 2. So slope 2 basically means that every time I increment my x by 1, my output is going to be incremented by 2 units. So every time I add 1 unit to x, I have to add 2 units to y. So this 2 basically coming from here, this 2 coming from here. And so every time I increment my x by 1, you can see that this is 0, 0 plus 2. This is 0 plus 2. This is 2 plus 2. This is 4 plus 2. This is 6 plus 2, and so on and so forth. So this function behaves like this. So now let's go over here. This is actually a good example. And it says, from table 2, being basically this table, we can infer that for these two functions, exponential growth dwarfs linear growth. So that basically means that for up to, let's say, up to x is equal to 2, your outputs are more or less the same. But from x is equal to 3, this function starts rising very rapidly, 8 to 16 to 32 to 64. But this function is just doing very slowly, 4 to 6, 6 to 8, 8 to 10 to 12, and so on and so forth. So the growth in this exponential function is much more rapid than the growth in this linear function. So basically, in exponential growth refers to the original value from the range increases by the same percentage over equal increments found in the domain. So basically what that means, the original value from the range increases by the same percentage. So that means that multiplying by 2, that means 100% growth. So 100% growth, again 2 plus 2 is equal to 4, right? 100% growth here. So when I multiply by 2 here, I have the same percentage being multiplied by this member of the range, and that makes this the next member of the range here. And that is over equal increments found in the domain. So the increments here are equal. So this is +1, this is +1, and this is +1. So over equal increments in the domain of the function, I have basically the original value from the range is being increased by the same percentage over equal increments in the domain of the function. So I have to continue the rest of this in the next video.